I have uncovered sonic, health attacks, voter tampering, and weapons used against targeted individuals are real and covered up because its foundation is made with GPS generator signal L1 1575.42 MHz, rubidium atomic clock generator, frequency comb generator which produce 3 lasers, diode signal, diode coupling, and diode probe 1550 which MILITARYS around the world uses satellite microwave radiation quantum optics A.V. vapor surveillance and torture. Arellano Familia. 82459 Deborah Drive A. Indio, California 92201. 760-812-3942. iRecorder. GPS. Signal carriers. The GPS satellites transmit signals on 2 carrier frequencies. The L1 carrier is 1575.42 MHz and carries both the status message and a pseudo-random code for timing. Frequency can be added to the L1 1575.42 MHz using BPSK method. These added frequencies keep all the same properties and the GPS signal gets added. A communications. Radio frequency is an area used in communication devices such as transmitters, receivers, computers, televisions, and mobile phones, to name a few. Radio frequency is also applied in carrier current systems including telephony and control circuits. Yeah, this is no joke. The L2 carrier is 1227.60 MHz and is used for the more precise military pseudo-random code A. Pseudo-random codes. There are 2 types of pseudo-random code. See tutorial for explanation of pseudo-random codes in general. The first pseudo-random code is called the CA course acquisition code. It modulates the L1 carrier. It repeats every 1023 bits and modulates at a 1 MHz rate. Each satellite has a unique pseudo-random code. The CA code is the basis for civilian GPS use. The second pseudo-random code is called the P precise code. It repeats on a 7-day cycle and modulates both the L1 and L2 carriers at a 10 MHz rate. This code is intended for military users and can be encrypted. When it's encrypted, it's called Y code. Since P code is more complicated than CA, it's more difficult for receivers to acquire. That's why many military receivers start by acquiring the CA code first and then move on to P code. Navigation message. There is a low-frequency signal added to the L1 codes that gives information about the satellite's orbits, the clock corrections and other system status. There are several good reasons for that complexity. First, the complex pattern helps make sure that the receiver doesn't accidentally sync up to some other signal. The patterns are so complex that it's highly unlikely that a stray signal will have exactly the same shape. Since each satellite has its own unique pseudo-random code, this complexity also guarantees that the receiver won't accidentally pick up another satellite's signal. So all the satellites can use the same frequency without jamming each other. And it makes it more difficult for a hostile force to jam the system. In fact, the pseudo-random code gives the DOD a way to control access to the system. You would think this would be true, but the satellite can be bypassed by creating a spoof GPS signal which our military does every day. Rubidium atomic clock. An atomic clocker is our clocker device, time standard, that uses our hyperfine transition of frequency in the microwave or electron transition of frequency in the optical or ultraviolet region to or of the electromagnetic spectrum O for atomsa as our frequency standard for its timekeeping element. Atomic clocks are the most accurate Timian frequency standards known, and are used as a primary standard for international time distribution services, to control the wave frequency of television broadcasts, and in a global navigation satellite system such as a GPS. Rubidium, soft silver metal. AAA, soft silver metal. According to a 2015 study by Ruth H. Zadig al., a group of physicists and chemists from across Europe and Asia, published in Science Advances, rubidium was introduced into a buckyballs A carbon-60 molecules, rearranging the atoms into a new crystalline structure. The new structure showed a combination of properties including insulating, superconducting, metallic, magnetic, and what is known as a yarn teller metal. A yarn teller metal is a metal that can be transformed from an insulator into a conductor by applying pressure. Although a second is defined by the oscillations of a cesium atom, oftentimes rubidium is used in atomic clocks, according to a periodic table, due to a less expensive price tag. Several studies, including those done by ESA and a Chinese researcher, discuss using rubidium clocks on satellites, spacecraft, and on laser guiding systems where precise timing is needed. Rubidium has 2 naturally occurring isotopes, rubidium-85 and rubidium-87. Rubidium-87 is a radioactive isotope is used to determine the age of old rocks. It has a half-life of 49 billion years. It is also used as a frequency standard in high-accuracy timing equipment such as GPS receivers. It is also used to produce Bose-Einstein condensates and in laser cooling. Optic frequency comb. Optical frequency combs were developed nearly 2 decades ago to support the world's most precise atomic clocks. Acting as precision optical synthesizers, frequency combs enable the precise transfer of phase and frequency information from a high-stability reference to hundreds of thousands of tones in the optical domain. This versatility, coupled with near-continuous spectroscopic coverage from microwave frequencies to the extreme ultraviolet, has enabled precision measurement capabilities in both fundamental and applied contexts. This review takes a tutorial approach to illustrate how 20 years of source development and technology has facilitated the journey of optical frequency combs from the lab into the field. Introduction. The optical frequency comb, OFC, was originally developed to count the cycles from optical atomic clocks. Atoms make ideal frequency references because they are identical, and hence reproducible, with discrete and well-defined energy levels that are dominated by strong internal forces that naturally isolate them from external perturbations. Consequently, in 1967 the International Standard Unit of Time, the SI second, was redefined as 9,192,631,770 oscillations between two hyper-fine states ENA 133 Cs1. While A133C's microwave clocks provide an astounding 16 digits in frequency, time accuracy, clocks based on optical transitions in atoms are being explored as alternative references because higher transition frequencies permit greater than a 100 times improvement in time, frequency resolution, CAO timing, synchronization, and atomic clock networks. Optical signals, however, pose a significant measurement challenge because light frequencies oscillate 100,000 times faster than state-of-the-art digital electronics. Prior to 2000, the simplest method to access an optical frequency was via knowledge of the speed of light and measurement of its wavelength, accessible with relatively poor precision of parts in 107A using an optical wavemeter. For precision measurements seeking a resolutions better than that offered by wavelength standards, large-scale frequency chains were used to connect the microwave definition of the Hertz, provided by Thea 133C's primary frequency reference near 9.2 AGHz, to the optical domain via a series of multiplied and phase-locked oscillators too. The most complicated of these systems required up to 10 scientists, 20 different oscillators and 50 feedback loops to perform a single optical measurement. Because of the complexity, frequency multiplication chains yielded 1 to 2 precision optical frequency measurements per year. In 2000, the realization of the OFC allowed for the replacement of these complex frequency chains with a single-mode locked laser MLL, enabling vast simplification to precision optical measurement and rapid progress and development into optical atomic standards. OFCs were developed by drawing on single-frequency laser stabilization techniques and applying them to mode-locked pulsed laser systems. The result was a system that could synthesize 105 or 106A harmonically related optical modes from either an electronic or optical reference with a fidelity better than 1 part in 1018. More importantly, OFCs enabled the direct conversion of optical to microwave frequencies and vice versa, enabling the extraction of microwave timing signals from optical atomic clocks. Beyond their application to precision optical metrology, OFCs were quickly recognized for their versatility as high-fidelity optical frequency converters and as sources of precisely timed ultra-short pulses. More broadly, by taking advantage of the non-linearities possible with the ultra-short pulses, OFCs enable synthesis over broad spectral regions including the near-infrared, the visible domain and as far as the extreme ultraviolet XUV. Generation of difference frequencies within the optical spectrum also allows for high-fidelity frequency transfer to the mid-infrared, terahertz, and microwave domains. OFCs quickly found application to a multitude of diverse optical, atomic, molecular, and solid-state systems, including X-ray and the TOSCON pulse generation 4, coherent control in field-dependent processes 5, 6, molecular fingerprinting 7, trace gas sensing in the oil and gas industry 8, tests of fundamental physics with atomic clocks 9, calibration of atomic spectrographs 10, precision time, frequency transfer over fiber in free space 11, arbitrary waveform measurements for optical communication 12, and precision ranging 13. To support this broad application space, OFCs have seen rapid changes in laser development to enable coverage at different spectral regions, varying frequency resolutions, and to enable the development of systems that offer lower size, weight and power, SWaP, 14, 15, 16, 17. The remarkable technical capabilities outlined above gained John A. O'Hagan A. Hall and Theodore H. Ansch recognition by the Nobel Committee in 2005 for their lifelong contributions to the field of precision optical frequency metrology 18-19, as well as for the technical vision and expertise that resulted in the realization of the OFC 20. A quick search on Google Scholar for publications that contain the exact phrase AOEOFC returns more than 14,000 publications on the topic in the last 20 years. In writing this review, we hope to provide a broad historical overview of the origins of OFCs, explain how they work and how they are applied in different contexts. More importantly, we hope to motivate the reader as to why frequency combs are such a powerful tool in the context of precision laboratory experiments, and explain how they are moving beyond precision metrology and toward commercial applications. What is an OFC and how does it work? The traditional answer is that an OFC is a phase-stabilized MLL. While different generation methods have been developed over the past 20 years, MLLs were the original OFC sources. Because of their historical relevance and operational simplicity, we use them here as a starting point to explain the basics of OFC generation. The utility of MLLs within the context of optical metrology was recognized as early as the late 1980s. The optical pulses from MLLs result from the coherent addition of hundreds of thousands to millions of resonant longitudinal optical cavity modes, spanning up to 100 nanometer in the optical domain. While the broad optical bandwidth is immediately attractive for spectroscopic applications, the mode-locked optical spectrum has unique properties that are beneficial for precision optical metrology. 1. All the optical modes are harmonically related, perfectly equidistant in frequency, and 2. All optical modes are phase coherent with one another, share a common phase evolution. The consequence of this is that the evolution of the electric field, and consequently the phase and frequency dynamics of every optical mode in the laser OFC spectrum is deterministic. As a result, knowledge about the absolute frequency of one mode can be used to determine the absolute frequency of any other mode. Optical frequency comb tied to a GPS signal. Jack A. Stone and Patrick Egan. https://www.ncbi.nlm.nih/pmc/articles/pmc/articles/pmc4548864/#!. Ho equals 5.86420. This is the main component of control, captivity, the plain flat-out birth of the surveillance and weapons portion of this device. By making an electromagnetic phase-locked loop, this is also the portion where the added audio frequency rapida around coupling laser and probe laser 1550, radio frequencies over fiber ROF to become a fiber optic C-band signal with audio and video. Optical frequency combs can be employed over a broad spectral range to calibrate laser frequency or vacuum wavelength. This article describes procedures and techniques utilized in the Precision Engineering Division of NIST, National Institute of Standards and Technology, for comb-based calibration of laser wavelength, including a discussion of ancillary measurements such as determining the mode order. The underlying purpose of these calibrations is to provide traceable standards in support of length measurement. The relative uncertainty needed to fulfill this goal is typically 10^8 and never below 10^12, very modest requirements compared to the capabilities of comb-based frequency metrology. In this accuracy range, the Global Positioning System (GPS) serves as an excellent frequency reference that can provide the traceable underpinning of the measurement. This article describes techniques that can be used to completely characterize measurement errors in a GPS-based comb system and thus achieve full confidence in measurement results. Digital phase-locked loop. Phase-locked loop (PLL) and digital phase-locked loop (DPLL). This is generated with the frequency comb generator and GPS generator. At this point, the rubidium clock starts to join in and provides control to the GPS for movement, manipulation and control of GPS and digital phase-locked loop, which is involves target in a cavity where rubidium clock fills cavity with rubidium-87 atoms, which are radioactive TARTGET plus radioactivity. That's a conducive to healthy living. Also, radio frequencies over fiber starts at this point. https://abdn.ac.uk/users/gori/course/fi-pages/dpll.html. A phase-locked loop (PLL) is an electronic circuit that controls an oscillator so that it maintains a constant phase angle relative to a reference signal. In communications, the oscillator is usually at the receiver, and the reference signal is extracted from the signal received from the remote transmitter. Phase-locked loops are widely used in space communications for coherent carrier tracking and threshold extension, bit synchronization, and symbol synchronization. What is radio over fiber? https://www.fiberoptics4sale.com/blogs/archive-posts/9504307/-radio-over-fiber. What is radio over fiber ROF? Radio over fiber (ROF) refers to an analog transmission over fiber technology whereby light is amplitude modulated by a radio signal and transmitted over an optical fiber link to facilitate wireless access. Although radio transmission over fiber is used for multiple purposes, such as in cable television, CATV, networks and in satellite base stations, the term ROF is usually applied when this is done for wireless access. In ROF systems, wireless signals are transported in optical form between a central station and a set of base stations before being radiated through the air. Each base station is adapted to communicate over a radio link with at least one user AS mobile station located within the radio range of said base station. ROF transmission systems are usually classified into two main categories, RF over fiber, AF over fiber, depending on the frequency range of the radio signal to be transported. In RF over fiber architecture, a data-carrying RF radio frequency signal with a high frequency, usually greater than 10 GHz, is imposed on a lightwave signal before being transported over the optical link. Therefore, wireless signals are optically distributed to base stations directly at high frequencies and converted from the optical to electrical domain at the base stations before being amplified and radiated by an antenna. As a result, no frequency up-down conversion is required at the various base stations, thereby resulting in simple and rather cost-effective implementation is enabled at the base stations. In a RF over fiber architecture, an intermediate frequency radio signal with a lower frequency, less than 10 GHz, is used for modulating light before being transported over the optical link. Therefore, before radiation through the air, the signal must be up-converted to RF at the base station. Zeeman effect. This effect ushers in warmed rubidium and basically formats every atom and photon where it needs to go with the electrical energy from the digital phased locked loop electromagnetic wave. The atomic energy levels, the transitions between these levels, and the associated spectral lines discussed to this point have implicitly assumed that there are no magnetic fields influencing the atom. If there are magnetic fields present, the atomic energy levels are split into a larger number of levels and the spectral lines are also split. This splitting is called the Zeeman effect. http://www.par.rochester.edu/blackman/as104/Zeeman-split.html. So you have been introduced to the 3 generated. Now I am going to show you how 3 diode lasers produced with a frequency cone generator and dispersed and joined with the GPS produced radio frequencies producing ROF, and we are going to talk about quantum optics, audio, video nonlinear communication and surveillance. We will also uncover the weapons used on people WHO are being GANGSTALKED, and the people WHO have experienced sonic health attacks. I promise you it is not SCCADAS and OR crickets. We left off with rubidium atoms and photons finding their places in the electromagnetic cavity called phase-locked loop. Now 2 lasers are introduced, diode COUPING laser 808 nanometers, which is a push laser which basically pushes things along. Definition: diode laser devices where the generated light is coupled into an optical fiber. Alternative term: pigtailed diode lasers. More general term: A diode lasers. German: A Phase-gekoppelt Dioden laser. Categories: A. Fiber optics and waveguides, A. Lasers. How to cite the article, A. Suggest additional literature. Author, A. Drive. RA 1/4 digit hashotter. https://www.rp-photonics.com/fiber_coupled_diode_lasers.html. Next we have a probe laser 1550 nm, which is a pulse laser. Imagine strobe light or an old flashing film projector with a light flashing like an old-fashioned flash on a Polaroid camera. Every time it flashed, an image is imprinted onto the laser. At the speed of light it becomes a flip page-like animation, all at the speed of light. A. Doppler cooling. Now we have the probe and coupling laser working together, and they produce Doppler cooling, which can slow light from 186,000 miles per second to 38 miles per hour. Doppler cooling is a technique for a laser cooling of small particles, typically atoms or ions. The basic principle is theta absorption and subsequent spontaneous emission of photons to lead to light forces, and these forces become velocity dependent through the Doppler effect. An absorption resonance of an atom or ion is shifted, e.g., towards lower frequencies when the particle is moving towards the light source. For example, a beam of atoms in a vacuum chamber can be stopped and cooled with a counterpropagating a single frequency laser beam, the optical frequency of which is first chosen to be somewhat higher than the atomic resonance, so that only the fastest atoms can absorb photons. Subsequently, the laser frequency is reduced so that slower and slower atoms participate in the interaction, and finally all atoms have a greatly reduced speed, at least in one dimension. This corresponds to a lower temperature, assuming that thermal equilibrium can be re-established. An alternative to sweeping the laser frequency is sweeping the atomic resonances via a spatially varying magnetic field, Zeeman slowing. Electronically induced TIANSPATENCY. Now let's talk about the third laser, the signal laser 180 nanometers. This is an infrared laser, so it's a coupling laser. The A signal laser brightens up a whole area of frozen atoms and photons producing a LECTONICALLY induced transparency BASICLY, cleaning the blackboard, casting a shadow of its surroundings onto a photon, now creating electrically induced absorption. Electromagnetically induced transparency, absorption, and microwave field sensing in RV vapor cell with a 3-color all-infrared laser system. https://journals.aps.org/pra/abstract/10.110.3/physriva.100.0634227. How Rydberg atoms work and produce GPS, rubidium atomic clock, and frequency cone generators and diode laser signal, coupling and probe. Now this talks about TIAHERTZ imaging probe laser ISO 1550A wavelength in nanometers equals a 5.1702 at 10 to 27 terahertz. https://its.com/technology/electronics/quantum-sensors-using-rydberg-atoms-enable-ultra-sensitive-extremely-wide-band-electric-field-sensors-communication-receiver/. https://physicsworld.com/a/high-speed-terahertz-imaging-system-uses-rydberg-atoms/. Quantum entanglement is casting an image on 2 photons and it calls a chain reaction and multiples on more photons. Quantum entanglement is thought to be one of the trickiest concepts in science, but the core issues are simple. And once understood, entanglement opens up a richer understanding of concepts such as the many worlds of quantum theory. https://www.quantamagazine.org/entanglement-made-simple-20160428/. Image is imprinted onto the probe laser 1550 and is converted to AC band 1550 nanometers glass tube, and now video and audio can be sent anywhere in the world.
Thank you. I hope this was informative. My name is Anthony Ariano. Hopefully we can get some help soon. Thank you.